Hello, everyone, and welcome to this special seminar that will be given by François Dulieu, who is an expert on experimental astrochemistry. He obtained his PhD in atomic physics from the University of Paris-Saclay. And then he joined the Paris Observatory and the University of Cergy, Paris, close to Paris, where where he's the director of the experimental laboratory of ICES from LIRA, which has different locations. So he's the director of the location of LIRA in the University of Cergy, Paris. So he will explain us about the work that they do there, about ICES of astrophysical interest and the astrochemistry involved there. So it's pretty similar from what they do here at CAP in the ICES laboratory from Guillermo Muñoz Caro. Yeah, so I hope that you like the seminar, and thank you very much, François, for being here.
Thank you very much for the invitation, and I'm here also thanks to the organization of an astrochemical workshops. It's really my pleasure to have the opportunity to present my work in a more general way than I did for the sulfur chemistry. So I won't speak about the sulfur chemistry in particular, but I will have a broader scope and try to explain why we do this kind of experiments, how we do it, and what are our main findings. So basically, you see this picture, which is a montage, which is called Venus, so toward new synthesis in French. So you could see directly with this montage that the pink color there, which is hydrogen Balmer, is the same that's the one we use here. Not as a lamp, UV lamp like in CAB, but as a source of atomic hydrogen. So I like to start with this trick. This is, it's in French. I hope that I would have a translate. Okay, anyway, that's, I think, not that a problem for Spanish people to have some French. Hopefully, okay, sorry. So that's one planet in the infrared, and this is the same planet in the visible. So this is how the astronomer work. They use as many information as possible, and they have to pay attention to the interaction, of course, of the matter. So if you want to explain what is optical thick and thin lines, just have this idea. So it's also why it's better to have the telescope high in altitude, and also that's a way to speak about the greenhouse effect. So the same trick, looking at the pillar of creation. If you go in the visible with the HST, it's not the same that if you have a combined picture from there, because you change the opacity of the media and you can get through and see the background stars. What is scattering the visible light is the same process that the cloud in our sky. If you have solid particle, you will have scattering, and you can directly from that infer the size of this solid matter. So each time you see beautiful shapes in astronomy, it's because it's smoky, dusty, dirty. It's important. So these are aggregate from planetary dust particles. So actually, the particle that scatters and that makes the shape of the clouds are the small part of this larger grain. Because okay. And now, now we understand well how we go from the visible to the infrared, we change the transparency of the media. So in the visible, you see here a hole in the sky. Of course, it's not. Is it working? I need to be patient. Okay, it was out of the scope. So it is not a hole, of course. And then if I move the next step, we go zoom in, but also we shift toward visible, even far infrared, and even above. And then inside, this is a star-forming region, or you have just the star of a burst. So it's a direct information to see that actually it's weird to see that it is where it's very dark that the star can burn. And it is also where you can see an explosion of the molecular diversity. So actually, you probably may all know these kind of things. But what I want to point out here is that actually the microphysics, so at the very atomic scale, has also a very large impact on the total life cycle of this gigantic structure. So I will try to go there. And if you look at in more detail on what we have seen, so here you get the star which is embedded, and so you have your telescope because you want to be above, because you want to look in the infrared. So everything here is CO. But here it's very broad. Don't look at the color. It's very broad. And here you see the rotational line of the same molecule, which is CO. So you see directly that from this line of sight, you have not much of CO in the gas phase, while there you have a lot of CO in the gas phase. It's because basically this system is already hotter inside, and then you have a sum of different regions. That's also a problem for, that's one of the major difficulty of observing the molecule. But from that, you directly know that there is an interplay of the gas and the solid phase, and you cannot really do astrochemistry, so the study of molecule in the universe, without taking into account both phases. So again, if you look at any cloud, it's not the same cloud, but don't worry, the same idea. And look any star behind these clouds, you will find a typical spectra like that, where you will find the molecules, the most abundant in the solid phase, which are water, CO2, CO, and some methanol, for example. And so the purpose is to understand how these molecules are formed in this media, and we do directly see that they can also be stored in the gas phase. Oh, does not work like it should. Okay, it works exactly at the opposite direction. So it's all scooped. So my joke about sulfur is done. Okay. So that's the astrochemist, and the size is the number of atoms. So basically, if you want to do chemistry, you have to pay attention to H, because it's the very large fraction of the atom. And then if you want to do something more interesting than H plus H, so I studied a lot, but today I will not speak about, because it's the most possible, probable, and abundant reaction that also drives the energy budget of this media. Then you will associate with oxygen, which is the second one, then to carbon, then to nitrogen, and then you have our sulfur, if it's your favorite one. But actually, it's smaller than the silicate, so very small dot. I made it larger there, but it does not work, sorry. So, of course, the story of astrochemistry is mainly driven by not the solid phase, but by the rotational, the radio astronomy, which has access to the rotational, as you certainly know, and then you can go deep in the detail of the shape of the molecule. And here I just pointed out that formamide, which is quite a complex molecule, was already detected in the very early time. So it means that it's kind of common, very common molecules. And now here there are people that are really molecular hunters, and that could find with the next generation telescope many more complex molecules. But in the general speaking, we know now that the atoms are made at the interior of the star. So for example, the oxygen in red, nitrogen, carbon in gray. And then there is a first accretion time where you do from solid particles, which are the dust grains. So let's say silicates or carbon amorphous silicate, depending on the star. And then later, there is a secondary freeze out of the atoms on the grain, and then you start to form molecules then that can be released to later to different astrophysical objects, such like planets and like our. But the point is that you cannot, molecules out of the Earth, for example, cannot survive very long because it's really photolysed rapidly. So you need to have a molecule that survives in space to be UV shielded, and then that's the point. See, if you UV shield, then the matter will cool down, the grain will be very cold, so the gas will accrete on the grain, and then you know by definition that even if the molecules are not formed on the grain, they survive only where you have the very cold conditions. So actually, the solid phase is the reservoir of the chemical complexity that you can get retrieved when you analyze sample return missions or a meteorite on Earth, where the molecular complexity is huge. And then I will go back to the beginning of the story, where you have a nitrogen world and a dust grain. So the dust grain is typically 0.1 micron with 10 to the 6 adsorption site. So what is an adsorption site? It's approximately the size of an atom on this grain. So now if we move on, the most probable event is that one hydrogen atom comes and stick on the grain. Actually, it sticks, and it's a little bit a boring story. It will scan, so you need to study the diffusion, and every millisecond it does an hop and visit. So in a million of seconds, typically, it will make a round of all the grain. And we studied also the other atoms, such as the oxygen and nitrogen. And now, if we have an oxygen atom, then it moves, and we need to wait for a nitrogen atom to form a molecule. And that was the idea to study the formation of water there, because oxygen is the second most abundant atom in the universe. So if you continue the story, it has an end where there is no more oxygen in the gas phase. And this corresponds to typically 10 to the 100 layers, so few tens to hundreds layer, 100 layers, and it happens quite rapidly in this media, so 10 to the 5 year, while the evolution of the cloud is probably 10 times longer, depending on the size of the star. But okay, this was in French. Okay, I skip. Now, the question for our group, that's exactly what we are doing every day. We want to understand how the molecular complexity can develop on grain. And because we are lazy, we don't want to make it too complex, so we would have no energy. So that's the main difference between here and our group, that we don't add extra energy. We just start from atom or molecule and see how it works. So we will have an accretion phase, a diffusion phase, a desorption phase, and possibly we want to pay attention to the energy of the reaction that could change also the ice morphology and so on. But that's exactly what we want to do. So that's our purpose. And in principle, it's not that complicated. You just need cold surfaces, you just need atoms, and you just need a way to detect them. So for the cold surface, it's quite simple. You need a cryostat, and you need also a sample, which is here. And then this is a spray if you want to deposit, for example, another molecular layer, such as water. So if you deposit water, you can change the shape and the morphology of the water. Here it's crystalline or amorphous. And basically, I will speak about monolayer later. And what is a monolayer? It's when you fill the surface of atom, so everything is covered. So the orange dot are the adsorption. So sorry, the green dot are the adsorption sites, and the red dot are the connection between the adsorption site. Basically, a monolayer is reached when all the green dots are covered with an adsorbate. And depending on your community, we could speak about millieV or kg per mole or Kelvin for the astronomer. So choose your unit. The atoms is a little bit much more tricky because oxygen atoms are not provided in bottles. So you need to pay attention to that. So basically, we will provide plasma to decompose the molecule, and then we have atoms, atomic peak. I will get back. And to observe them, same technique as in many labs there, we use infrared in grazing angle, and we use also, so this is an example, you co-deposit the molecular oxygen and nitrogen oxygen, and they react directly at 10 Kelvin, and then you have a nice spectra. So it's good, it's cool, but for example, the O2 molecule has no infrared band, so you cannot follow the oxygen. You know that it works because you have a reaction. Then you have something which is not has no difference of sensitivity or not much, which is the Q mass. The point that the Q mass is in the gas phase. So we only record things in the gas phase, but in our setup, we have different way to observe the molecule in the gas phase. So I will go later in this detail. So it is like my lab was actually 10 years ago. It has changed because now there is no such a disorder. No, it's not true. It's still disorder, but not the same one. So this is my main colleague, Emanuele Congiu, which is working. Ciao, Emanuele. Yes. And it is one of our setups there, which is formalism. I will show you some results with this formalism. And it's in the background, but in the foreground, this is the electronic to drive the experiments. So this is Marco Minisale, my PhD student. So again, ciao Marco, we are here, please. He's trying to do, an oxygen beam. And so the oxygen is now flowing in this pipe here. It makes a spark, and then because you have a microwave frequency, you have a very white, it is not hydrogen, it's oxygen, beam, but it's in a millibar. And you want to send the oxygen atom not in a millibar, but in a 10 minus 10 millibar zone. So you need to go from the bottle to the main chamber. And all these complicated things is to go from the millibar, which is here, to -3, -7, -9, and then, we are -10 millibar. We are happy with that. And we have our it's not very visible, it's there. And you can see a hazard detection setup. But anyway, it works like that. It's not that complicated. So the first experiment is exactly what we have in the video. Is you expose the oxygen atom and you cool down the surface. So, and you look at with the Q mass. So the signal is not what is in the beam, not what is in surface, but the interaction of both. So basically, it's all in the gas phase. So the atom, they could get in the surface and get out there. So when the surface is 100 Kelvin, the oxygen, they get in and out. And at some point, you get a freeze out. The oxygen stick on the grain, and you don't see them anymore in the gas phase. It's really a freeze out like in Astromedia. And then with the Q mass, you can switch to O2, and you see that O2 is raising when oxygen is on. And if you look in the infrared, you will see exactly this point. You can detect the ozone. That's when the O2 stick on the grain. And you can follow with the infrared the same experiment, and you see that the ozone is formed at very low temperature, so 8 Kelvin, and even if you have very, very low coverage, so 0.1, 0.2 Kelvin, you can start to form ozone, meaning that the atom, they can meet and react on the surface even at 6 Kelvin and below 0.3 monolayer coverage. So if you do an experiment putting more and more and more oxygen and then doing a TPD. So a TPD is you start from a low temperature, you expose the atom, and then you heat and you record in the gas phase what happened. And you see clearly that in this case, when the surface temperature was hot, hot is 30 Kelvin for me. The oxygen, they mostly form ozone, that's the green curve, while if it's 8 Kelvin, it's in the black curve, it's mostly O2. So why so? It's because if you have a large diffusion, when an oxygen atom comes, it will move and form O2, and then the next one will form O3. So at the end, if it's very fast, you will have a lot of ozone, while if it's cold, the atom, they can stick, and then stay as O2 mostly. So doing the balance between O2 and O3, it's possible to access the kinetics. That's what we did for different substrates. So we all know that ice is slippery, so also at 10 Kelvin it works. So the diffusion is an order of magnitude faster on water ice than on silicate or graphite, which is a surprise, but it's what we measure. And then the other surprise is that it was modeled as an exponential law, and clearly the exponential law, so Arrhenius law, does not work. So we said, okay, it really looks like it would be quantum tunneling. And then if you make a computation classical, you see that it fairly reproduces the data. And if we had a point at high temperature, doing another, it works quite well. So now we know how it works. Let's complicate things. Now we will use two atoms to see if we can form water. So the idea is simple. In principle, if you add hydrogen, so white arrow is +1 hydrogen, you go from the oxygen to the water, and we know that the H can do H2. And actually, we could see that it worked, but actually we realized immediately that you could form the ozone, and so the chemical network is not at all that simple. So actually, if you do an experiment which is just oxygen plus hydrogen, you already face all 14, 20 possible reactions. So we want to understand how it works to be sure. So you can use subsystems. So you can say, okay, I don't want to use both oxygen and hydrogen, but I can start from ozone, for example, and then I have less reaction. So I can study the ozone hydrogenation, we did. And if we are at 45 Kelvin, we say that the oxygen molecule can dissolve. So then the only possible way is this one. So we will see if it works. And actually, yes, more or less. From O2, we get, let's say, 100%. From ozone, that's the water signal. We get more. Good. 3 oxygen atoms from ozone, 2 oxygen from O2. It's good. But then at 45 Kelvin, okay, I told you one O2 molecule is desorbing, so I should have a third of the signal, but this is a very, very small third. So it's a real signal, it's not noise, but it's not a third. So it means that there is a lot of things which is missing. And why it is missing? It is because when actually a reaction occurs, there is a probability to get back in the gas phase. And that's really fortunate because then people doing radio astronomy can detect them with the radio telescope. If it was not working very well, everything stuck on grain, it would be very, very boring. And then to demonstrate that, we can put an oxygen layer, send hydrogen on the surface, and then when we send hydrogen on the surface, we do detect D2O. So we did not make it with hydrogen for confusion, but it's sure that what is desorbing is not OD, it's not OD2D, it's water mostly, which is desorbing when you send hydrogen atom over an O2 layer. That's the chemical desorption. So we did a lot of experiments, but at the end, we realized that if you take this arrow as the energy available when you send an oxygen atom, and this one, the energy available when you have an hydrogen atom, and you look at the enthalpy of formation of the molecule, so this one is less stable than that one, you understand that the water is the most stable molecule in the system, and actually that you have enough energy to go from any point to any other point. So at the end, if you put a kind of randomly oxygen and hydrogen atom on the surface, you will end up with water. So water in this system is always formed, and it's what I call a chemical attractor. It's a trap to oxygen and hydrogen atom. You can have other detail as the morphology of the ice form is very compact and it is amorphous and that. So now you understood we have worked with 2 atoms. Let's input a third atom like carbon, for example. No, nitrogen, sorry. Okay, nitrogen. So we can do the same. And so that is called a co-decomposition. So the sketch is that when I put a bracket, I do it at the same time like that. And then I do a TPD and I observe the hydrogenation of this molecule, but also some N2O and water. But it was known before. And now with that, you can say, okay, I can study how deep the hydrogen goes down. So to do so, you put NO first, and then you put hydrogen. And you see your infrared signal is reduced because your NO is just consumed by the hydrogen. And so how deep it goes, so you put a layer under a layer of NO, small, larger, larger, and larger, and you look at the infrared decay, and you see that when it's kind of thicker, the decay is not to zero. It means that you only go and attack the first upper layer of your sample. So the consumption is this blue arrow, red arrow, I did not draw. So if you put it on a line, you see that your absorption or NO consumption is this one. And if you cross with the total absorbance of the NO you get, this is exactly the monolayer you derived. So actually, the hydrogen is only scanning the surface, is only reacting with the first layer of the molecule, and it works for, depending on the structure of the surface, very well for NO and H2CO acids we tried. And then you can play with this game. You can add water, porous, I'm scooping the rest anyway. And study how the hydrogen is going deep through the water, and like an example. So now the carbon plus the nitrogen plus the oxygen experiment, when there is no hydrogen, H2CO and NO does not react, do not react. And then if we mix them together, there is no growth of H2CO and NO. They have disappeared. And what they did form this one, hydroxylamine, which is a result of NO plus H. This one, methanol, which is the result of H2CO plus H. And that one, which is formamide, which is a combination of both. So by putting these two molecules plus hydrogen atom aside, you can form quite a large fraction of formamide. And no other molecules. It's only formamide. And so, for example, no HNCO we were looking at. So we did the thing. So how we can understand that? We have a trouble there. NO will give rise to all these people on the surface, and CO will give rise to all these people on the system. So we did exactly how we did for the water. You cut the problem into pieces, you do many experiments, many conditions, and at the end, what is the driving force of this chemistry? Very strange. Any chemist could predict that, I would say. This is this radical, NHNO, attacking H2CO to form the formamide and OH. And if you compare what we have done on the gold and on the water, you see that on the gold, you can form quite a lot of methanol, while when there is water, you see that all the methanol is transformed into formamide. So it's like in this system with water, the main chemical route is not methanol as usually we do think, it's formamide, very efficient. So the question is, okay, is really formamide a very good and common chemical molecule? So we see that it's one of the first one we detected, and we can detect it in plenty of places. So I can define a little bit what I think my definition of a chemical attractor from my experiments. So basically, it's a molecule that should be resistant to hydrogenation unless I will maybe form it, but it will disappear rapidly. And it should be abundant, at least kind of almost the major output in some experiments. So for example, look at the CO2. CO2, you start from CO, you can form CO2. H2CO, you can also form CO2, and it's very efficient to go to CO2 starting from H2CO, adding oxygen atoms. So if we in our experiment, we find different ways to get to one specific molecule, we call it a chemical trap or attractor. So we found 4 of them today, but we made more than 50 different molecules in this kind of combinations. And methanol is not. Methanol is not chain end. We form a lot of time methanol, but we know that it will participate to further chemistry. I will go on that further chemistry. So we had a project with people in Grenoble, in Marseille, which is called solid interstellar radical chemistry, for studying the problem of chemistry, of radical. So, and that's why I will not speak about non-diffusive, non-radical, blah, blah, blah. There is a radical, and the radical, they can be formed inside the ice. In our experiments, we are only scanning the radical on the surface of the ice. But now, is it possible that you can transport the radical from a chemical point of view? So is the radical able to move or not, directly or not directly? That was the question we wanted. And then if so, do we observe some chemical convergency as we see like chemical attraction or something like that? So to recap the story of the CO formation, to understand what I will explain after, I remind you that you can go from CO to HCO, sorry, adding an hydrogen, but this HCO can also react with hydrogen and forming CO plus H2. And doing so, it will do some chemical desorption. You can also go to hydrogenation, but you see, each time you want to add one hydrogen in there, you have a chance to get back. And also, at each time we detect a methanol, we went through at least 2 different radicals. So when we do an hydrogenation, actually, for every 2 hydrogen, at least we have 1 methanol radical. And this is the energetical landscape of methanol. Methanol is a little bit much more stable than the 2 other, but not that much. So what I will show you, we call it the single radical chemistry. So is it possible to grow the molecular complexity using these radicals? So to demonstrate this, we did a simple experiment. So to know if you do one hydrogenation of H2CO and you look at the percentage level of what is formed, all that guys are formed. So I will not enter the detail, but you can, this is a nice guy you detect usually in your clouds. You can form all of them from just hydrogenation of H2CO. Now, a layer of H2CO12, a layer of H2CO13, not much of hydrogen, just to destroy a quarter of the first layer, not more. And we have seen that the chemistry is mostly on the first layer. And now, among these 2 carbon atom molecules, we look at some specific mass, and immediately we do see a 12 carbon, 13 carbon molecule. How is it possible? It's just because we do form a radical, let's say CH3O, and the CH3O will react directly with the H2CO, don't need to move. The C13 here is not moving, it's just this one is visiting that one directly. And so you can directly make complex organic molecules in one step. So with two hydrogen atoms and some H2CO, you get to one of your favorite complex organic molecule. Not necessarily the most abundant one, unfortunately, but anyhow. So the usual way I think it could work is the following. Your hydrogen going on the surface will meet any molecule that has, for example, a CH bond or a CO bond, and he has a chance to react. And if he reacts, he makes a radical. And next, this radical can have a neighbor, and this radical can react with the neighbor and make another radical that can react with the next hydrogen atom to make another molecule. So finally, it goes really faster if the neighbors are compatible, I would say. So this is what I would call also some non-diffusive chemistry, but you don't need a 3-body system. It's just hydrogen-driven surface chemistry. And you can form all the comps I spoke about. And that's, I think, how it works. So basically, I think that the radicals, they not diffuse, but they can transfer to go to more stable molecules that you can detect at the end. So then, okay, that's, yeah. The water is now have some complex organic molecule. So I try to have demonstrated you that actually the hydrogenation itself is a very strong vector for molecular growth, even though you can also destroy the molecule at the same time. And the fact that you have loops, so addition, abstraction, create radicals that can evolve toward different molecules you didn't thought about before. And that's how I think it works. And so, in general speaking, it's possible to form plenty of complex organic molecules this way, not every. And then the question for us is, which one would be a very good client for this hydrogenation route, and which one we don't detect very efficiently? So we could have surprise. So for example, we could form ketene, which is supposed to be something very reactive, and we were not the only one. So, and or glycol, whatever. And now we need to constrain, like we did with water, the chemical network, and to compare also if it's reasonable with calculations. And then also to find a way to insert them in the astrochemical model, because this scenario is not yet implemented in any of your favorite astrochemical code, but the work is in progress. So, it's French. Anyway, we studied also plenty of, no, I translated, so sure. Yeah, okay. There is also the English version. Okay. So we have studied also different aspects, like is it important that it is silicate or graphite or water? Yes, it is, but does not change the main story. There are other things I spoke, for example, during this week like the salts and the ionic bonds that could really change the chemistry. And but the general message I want to say is that in our case, what we do is we don't put energy, which is only a fraction of the story. So that's the very beginning of the story in very dark condition, and we explore the minimum pass energy pathway. So this is this picture. So we do not go through directly. We try to see where it goes, and some of the molecules, they pop out, like we form amide, and some other we don't, we are not able to achieve. So for example, the acids, can we produce acids in our experimental setups? Today, published in my group, the score is 0. Because it's not a real question. I mean, you have a hydrogen, very reductive condition, you want to do acids. Okay, does not work for today. Next time, hopefully, it will work. But in general, the molecules we are forming is the way to access to other world, and thanks to the activity of our colleague observer and modeler. And it seems that you can see that in our system, or you can see our system like it would be very, I mean, not modest to say that it works like a cell, then you can feed and evolve and store information. But at least we explore the selection rule of the initial chemistry, and to see that this selection rule has any chemical loops or cycle or open chemical systems as proper rule of evolution that we are investigating. And now the next challenge is, by the way, I showed you and nobody pay attention to that okay, in the astro ice, the 6 big guys we can see, among them, you get the CO2, the CO, and the methanol, and the methane. if you think about the CO or the C, this is the most reduced possibility, CH4, and the most oxidized CO2. And so we have a sample holder where we have the most reduced and the most oxidized part of the chemistry. If you're a chemist, you want to try to push things one way or the other, you then change the temperature of the pH. So I have not the right to change the temperature. I'm stick to 10 Kelvin, and it's fortunate somehow. And how can I change the pH? So maybe next year I will explain you. But today it's over. So I would like to show you my lab, which is a little bit like cab, not very easy. No, I mean, we have a direct train, that's the difference. Just 5 minutes by foot from Paris. So it takes, and everybody can enter also. And if you want to work with us or to have an idea to test in your sample systems, you're really welcome to collaborate with us. This is the colleague that made, and especially I show different results from all the world. So thank you for your attention.
Thank you very much for the very interesting talk. So do you have any question for François?
Very nice talk. Thank you very much again. I have a very specific question about this radical chemistry that you are describing in ices. You mentioned that it is not included in any of the astrochemical models?
It was included in one version of Grenoble by Vianney Taquet, but the secret is lost with him.
So when Jean Angarro and Chris Shingeldecker, they talk about non-diffusive, the so-called non-diffusive chemistry, it is not like that.
It's not exactly like that.
Okay.
Because they did not implement this kind of reaction. They did something more complicated in the sense that so you can look at the different mechanisms. So maybe not the Chris one is simpler, but anyway, from Garrod, it's more than you have a photon that excites your molecule, and because you have excited molecule, then you can react. So it's non-diffusive, but it goes in the bulk. So this is non-bulk. Or you form let's say a methyl group which is excited and again can move over the surface to have some diffusion. And in our case, I don't speak about that. I just say neighboring effect. So, and especially if we want to use the model to mimic the experiment, in the experiments, we are dominated by this neighboring effect. So it's important also to constrain that.
Yes.
And but to date, no, it's not. It's not. Okay. If I take Nautilus, I try to feed my data. I cannot because the process is not there.
Yep. No, but I would have thought that I mean, that's what first come to my mind when I imagine a nice reaction. So I would have thought that it was included already, but it's not.
Statistically, it could be included, but then you need to do the proper reaction. And usually they use two radicals to make a molecules. While here, I use one radical to be transferred in another radical.
Yep. Thank you. Thank you very much.
Thank you very much for the next talk. I have a couple of questions. So one is regarding the concept of chemical attractor. So if I have understood correctly, it's a molecule within a system of molecules which is thermodynamically favored and that cannot be easily hydrogenated, right?
Yes.
But what about the resistance or not to suffer hydrogen abstractions, for instance? Is this considered?
I think it's a key because I mean, for example, methanol is stable, and it's fully saturated. So you would say, okay, methanol should be the end of the story, but actually not. You could form comps from methanol, and actually it's a very good driver of comps. So that's why even we do form it, it's not resilient to hydrogen, meaning that it is a loop of the chemical system.
Methanol is a worse chemical attractor than formamide, for instance.
Yeah. So in what I say, yes, and the idea is yes, exactly.
Okay, and you mentioned diffusion of oxygen in your experiments, so
yes,
water and ozone. Have you also studied, can you tell about the comparison between nitrogen and oxygen?
Yes.
How they diffuse, how they compare?
We did not study the nitrogen in such detail because the trick with oxygen is to be able to compare ozone and O2. But for nitrogen, it goes to N2, and N2 is also in your beam. So it's very hard to achieve good results with N2. Anyway, we did an experiment where the same that we did with oxygen, at least to have a binding energy of nitrogen, and it's clearly really so the freeze out is not at 60 Kelvin, but it is at 30 Kelvin. So it's really one half, the binding energy is half. So the diffusion should be at least the same as oxygen and probably faster. So I would say that nitrogen is more mobile than oxygen for sure. And there is a difference also that in case of oxygen, the oxygen atom has a larger binding energy than O2, which is maybe not the case for nitrogen. So nitrogen could have not a very atomic nitrogen could have a low binding energy, less than the N2 that could also screw a little bit our experiments. So no detail on the real diffusion of nitrogen, but certainly I would be very surprised that it is not mobile at 10K from a grain perspective, meaning that you have a day or 2 days or 3 days before anything else happens. So I would say that nitrogen is surface diffusing for sure. Okay. And then, of course, because it's reactive, it will just visit few sites before it can mate with a molecule compatible.
Okay, thank you.
Are there any other questions?
Thank you. Hi, thank you for your presentation. I'm interested in the formation of glycoaldehyde and methyl formate. I was wondering, because you mentioned that the abundance ratio are not the right one. You briefly said that.
I mean, I know, yes, depending on the experiment, we can form more one of the other. So that's what we are trying to understand. What are the good candidates for us? So, for example, methyl formate is not the most abundant one we found in our experiments, depending on the condition. But we tried, like we see, with plenty of different conditions, while methyl formate is usually widely detected everywhere. So for example, I would have loved that the big guy just comes out from experiment exactly the same amount that what you or people observe in this condition, but it's not the case. So for example, we have methoxymethanol, which is very easily formed, and it is not so detected yet.
And
it is, but not as popular.
On the can you see the hydrogen destroying one of these species, for example? Or is it not possible at this?
No, it's what we have to do. But it's each time. I mean, one slide it could be 3 months of work. So but it's something we shall do quite systematically, but it will take time. So taking any of the big comps and shooting with hydrogen to see how they survive to this. And also that would be even better to see what is the fraction getting back in the gas phase would be really the standard goal for us. but each time is a complete study. Yeah.
Because right now what you see is how much is formed on the ice, but but you see it in the gas phase. So you have the binding energy that is taken into account?
So it's easy for us to determine the binding energy. It's easy for us to know that they were in the gas phase. It's almost impossible to detect them in the gas phase through chemical desorption, because as I show you for the water, the chemistry is very diluted, and we form not one comb but 12 of combs. Anyone that know how works Q mass, you can select any mass you want. You don't know what molecule it is. I mean, mass 29 is the most abundant, but it is for everyone. So at best, we say, oh, we have someone desorbing.
Okay.
And that's not very helpful.
Okay, thank you.
And something that nobody cares, we can easily chemical desorb the CO, but you don't care. CO is collecting very easily in the gas phase. This one I can put good numbers, but you don't care.
Thank you.
I had also a question about the formamide. So you say that it's a chemical attractor, no? But in the astronomical ices, it has not been observed yet, no? So do you know why?
Okay, so how to form following this prescription, how to form formamide, you need to have NO molecules close or NO chemical close to H2CO. And then if you do the statistic, you see that H2CO at 10 minus D8, NO is 10 minus 7. You do the statistic, you find that formamide is 10 minus 10 or 11. It's exactly what it fits with the observation. But then it's on the solid phase. It has a very high binding energy. So you need a region where you will put your ice back in the gas phase. So like a shock. In shock, paf, you get this formamide, which is easily formed on the grain, but you need some energetic event to put them back. So in hot, I would say, in region hot enough to put your ice back in the gas phase, as we do with TPD, you can observe the formamide. In a starless core or in prestellar cores, you need a mechanism that put the molecule back in the gas phase, and our chemical desorption is not efficient for this molecule because it is not looping and because it has a high binding energy. So it is the worst case, I would say, to find in prestellar cores. It's not impossible. You can then you need to have other extra energy, which would be cosmic induced sputtering or UV, but it's not very efficient. So this week I showed you a table for the good candidate or not the bad candidate at 10 Kelvin. And formamide was a bad candidate from this point of view. So it is not because I form it that I will find it in the gas phase. In this case, it has more chance to be included in the residue, and it's also known that you will find this organic compound residue. It is a good guy to form the residue because it survives the water sublimation. So we did experiments. You put a layer, and then that's the difference between the thin layer and the very big layers. So if you put a thin layer of formamide and over tenths of water molecule, you gently warm up. The formamide will dissolve way after the water.
But in the solid phase, the abundant will be too low to detect the absorption.
Yes. Oh yes. Minus 10.
Ah.
So compared to hydrogen, so compared to water, minus 6. Even in my experience, I can't detect it easily in the infrared. So no way.
And there's a question on Zoom.
Yes, the question is from Ismael Garcia Bernete. He is asking, thank you so much for the talk, amazing work. From the astronomical observational side, we are finding a lot of molecular ices and gas phase molecules in deeply obscure active galactic nuclei, where cosmic rays can penetrate high column densities and permeate the interstellar medium. Might be quite important enhancing molecule production. Are these considered? Again, thank you for the interesting talk.
I think it's considered in the fact that I said that the hydrogen is the main driver of the chemistry, but the hydrogen is only present because you dissociate the H2. So the driver of the H is the cosmic ray. It's or the secondary UV photon, which is the cosmic ray. But at the end, the hydrogen atom, you see, it will be there. Because if you have one secondary UV photon, it's because you have excited H2 molecule, and some of them will form H. Or even if you're a gas phase chemist, you say, okay, I have my H3+, but the H3+ actually also liberate one hydrogen atom. So basically, even if you have only 1/1,000 hydrogen atom, still, it's more than any other astrophysical quantum. So to answer, indirectly, you need the cosmic ray to trigger the H atoms that triggers the solid phase chemistry. So it's not direct input of the energy in the grain that would, that's another story. In my story, I need the cosmic ray to gentle derive the energy to the grain through the hydrogenation.
Okay, so thank you very much again, François, for the very, very nice talk.
Was my pleasure. Thank you.